So far in this chapter, we've gone over momentum and impulse and the idea of the conservation of momentum. Now it's time to look at elastic and inelastic collisions. There are two major types of collisions. First is a perfectly inelastic collision. This is a collision in which objects stick together after colliding. So you can imagine, for example, a football player that tackles another football player. The two would stay together as they fall to the ground. They would be stuck together down here in this conjoined mass. Now let's look at how momentum works in inelastic collisions. We have these two objects going into the collision, so we can call that mass times velocity of the first object plus mass times velocity of the second object. But now, because after the collision the objects stick together, their masses are combined. So we can think back to some practice problems in the last section, like where we had the two trains sticking together. And that will be multiplied by the final velocity of the two objects, which again will be the same for both objects, because the objects are now stuck together. And a note about inelastic collisions is that kinetic energy is not conserved. We'll look more at how this works a little later on. The second type of collision is an elastic collision. This is a situation in which objects collide with no loss of total kinetic energy, so both momentum and kinetic energy are conserved. And an easy way to remember this is something that's elastic returns to its former position, so you can think of the kinetic energy going back to the way it was before the collision. And objects in this situation typically bounce off of one another, so you can think of these two pool balls which collide in the middle and then go off their separate ways. So the way momentum works in elastic collisions, we have this initial momentum of the first object plus initial momentum of the second object, and then this sum will be equal to the final momentum of the first and the second object combined. This time the masses are not stuck together like they are in inelastic collisions. In most collisions in real life, it's important to note, are neither elastic nor perfectly inelastic. These are just situations we'll use for the sake of a few problems coming up. Practice number 1. A 1,500 kilogram car traveling at 15 meters per second south collides with a 4,500 kilogram truck that is initially at rest at a stoplight. The car and truck stick together and move together after the collision. What is the final velocity of the two vehicle mass? So first, the keywords in this problem to look at are stick together. This means it's an inelastic collision. So we can write the momentum equation as momentum of the car plus momentum of the truck equals momentum of the car and truck, or in other words, the mass of the car times velocity of the car plus mass of the truck times velocity of the truck will equal the total mass together times the final velocity. Now we're ready to plug in some numbers. Mass of car is 1,500 kilograms, and the velocity is 15 meters per second. The mass of the truck is 4,500 kilograms, but its velocity is 0, so this will go away eventually. Now we're looking for the combined mass of the two, so that'll be 6,000 times the final velocity. Now if we simplify a little bit here, we get 225,000 equals 6,000 times the final velocity. Divide both sides by 6,000, and the final velocity of the conjoined car and truck is equal to 3.75 meters per second, and we can remember that's to the south because that's the way that the car is initially moving. 2. A 0.25 kilogram arrow with the velocity of 12 meters per second to the west, here it's drawn to the east, strikes and pierces the center of a 6.8 kilogram target. A. What is the final velocity of the combined mass? So again, we're looking for the conservation of momentum. So we'll start with this initial momentum. The target starts at a velocity of 0, so it doesn't have any at first. So we can just say the initial momentum of the arrow will equal the final momentum of the arrow and the target. And again, this is an inelastic collision because the two objects are going to stick together. So now let's solve for the final velocity of the combined mass. We get that the initial momentum is mass times velocity, so that's 0.25 times 12. And that will equal the combined mass of the two objects, so that's 7.05 kilograms, and then we're solving for final velocity. Now we get that 3 equals 7.05 times v final. We can divide both sides by 7.05 to find that the final velocity of the two objects is 0.43 meters per second. In the second part, we're asked, what is the decrease in kinetic energy during the collision? So let's look at the initial kinetic energy first. So we know that kinetic energy is equal to 1/2 mv squared. We know that only the arrow has a velocity, so only the arrow will have kinetic energy. So we get 1/2 times 0.25, and then V is 12, so 12 squared is 144. That comes out to 18 joules. Now we'll solve for the final kinetic energy. Again, this will be 1/2 times mv squared. So we have 1/2. The combined mass will be 7.05 kilograms, and then we know from the problem before that the final velocity will be 0.43 meters per second squared. If we multiply all of this out, we get that the final kinetic energy is only 0.564 joules. Now if we're looking for the change, we can do final minus initial, so we have 0.564 minus 18, that's about negative 17.4. In other words, 17.4 joules of kinetic energy were lost during this collision. Number 3. A 4 kilogram bowling ball sliding to the right at 8 meters per second has an elastic head-on collision with another 4 kilogram ball that is initially at rest. The first ball stops after the collision. Find the velocity of the second ball after the collision. So we know that the mass of the first ball times its velocity plus the mass of the second ball times its initial velocity will equal mass of the first times the final velocity of the first plus mass of the second times the final velocity of the second. So let's plug in our numbers. We have the mass of the first, that's 4 kilograms, and its velocity is 8 meters per second. Mass of the second is also 4 kilograms, but it's not moving. And then in the end, the first ball has stopped, so now it's 4 times 0. The second one is still 4 kilograms, and we just want to find its final velocity. So we can simplify, get rid of these zeros. We get that 32 equals 4 times v final. We'll divide by 4 to find that the v final of the second ball is 8 meters per second. Now, since we're looking at an elastic collision, we want to verify our answer by calculating the total kinetic energy before and after the collision, and we know that it should stay the same because the collision is elastic. So, we'll look at before the collision first, that's 1/2 mv squared. We have the first ball, which is 4 kilograms, and it's moving at 8 meters per second, so we're going to square that. We get 2 times 64, or 128 joules. Now in the second scenario, again we have kinetic energy, which is 1/2 mv squared. This time only the second ball is moving, so we'll look at that. The second ball is 4 kilograms, and it's also moving at 8 meters per second. So if we calculate that, we again get 128 joules. Now we know that the collision was elastic, because kinetic energy was conserved. Practice number 4. Two objects move towards each other, collide, and separate. If there was no net external force acting on the objects, but some kinetic energy was lost, then they have all these choices with whether it was elastic or not, and whether total linear momentum was conserved. So first let's think about the type of collision. If some kinetic energy was lost, then the collision cannot be elastic. So we're going to eliminate choices A and B. Now we know from the law of conservation of momentum that momentum is always conserved in collision between objects. So D says it was not conserved, so we can get rid of D, and we're left with C. So this has been Chapter 6 of Physics, where we've looked at momentum and collisions. Thank you for watching.